I probably could have recorded all that, but just so it's on the record for the recording for anyone who's watching it, right? Our next test is 2 weeks from today. So not next Tuesday, but the following Tuesday. So this is sections, 11.4/11.6 continued. And I think I might have the other day even just called it 11.6. I can't remember. So we're going to talk about absolute and conditional convergence. So far up until today, we've just been talking about whether a series converges or a series diverges. And the series that we've been mostly looking at, when we've said that the series converges, we've actually been saying that the series converges absolutely, but we haven't actually kind of stated that. So we're going to talk about what these different types of convergence are. So first, I'm just going to give the definitions, so that way we kind of can go from there. So a series converges absolutely if the corresponding series of absolute values converges. And by that we mean, so we're right now, so a series, there's like the mathematical way of saying this. So the series, the summation of the a sub n's converges absolutely if the summation of the absolute value of a sub n's also converges. Okay, so you might go, well, we haven't really been doing stuff with the absolute values when we've been finding whether series converge or not. So how come you said that a lot of the series we did converges absolutely? So the reason that I could say that a lot of the series that we did converges absolutely is because when you're talking, a lot of the series that we've been looking at, all the terms have been positive. So if all the terms of the series are positive, then whether it's converges or converges absolutely, it's the same thing. So that's kind of why we've sort of been doing absolute convergence without actually like doing it. Conditionally convergence is a series converges conditionally if the summation of the a sub n converges, but the summation of the absolute value of the a sub n's diverges. So an example of a conditionally convergent series, right? So there's kind of like a pretty like well-known example, we'll say. So it's like, this is the example that's used all the time. So for example, we looked at the harmonic series and the alternating harmonic series. So the alternating harmonic series which was the summation n equals 1 to infinity of negative 1 to the n over n. So we looked at this series last time, and we found by the alternating series test it converges. So the alternating harmonic series converges. However, the summation n equals 1 to infinity of the absolute value of negative 1 to the n over n. That's actually just equal to the summation n equals 1 to infinity of 1 over n, which is the harmonic series. And we've looked at that a bunch of times, and we know that diverges, right? It's a p series. P is equal to 1. It diverges. So the alternating harmonic series converges conditionally. Conditional, well, that's terrible. Conditionally. So the alternating harmonic series, right? We know that converges, but when you take the absolute value of it and you look to see whether or not that converges or diverges, it ends up diverging, which means it converges conditionally. So to check whether something converges conditionally or converges absolutely almost always requires two tests, unless you get lucky, right? So if you check, so I pretty much always kind of start with the absolute value of a problem. So kind of to make you, well, does anyone need me to wait before I go to the next page? Let me start there. Sure, not a problem. So yeah, just let me know when you're ready for me to go on. Okay, no problem. Okay. So I'm going to draw kind of like a flow chart of how you do it. So if you're asked to check conditional or absolute convergence, there's kind of two ways you can start, right? So I'm going to show you the two different ways. So one thing is you can look at the absolute value first. So we'll check the absolute value of the a sub n. And then two things could happen, right? It could converge or it could diverge. If you look at taking the absolute value of the terms first, and it converges, then you're done. So when it converges, then you get to say, oh, this converges absolutely. If it diverges, then you have to also check, now you have to look at the original series. So the summation of the a sub n's. And then that original series could converge or diverge. If that original series converges, so the absolute value series diverges, but the original series converges, then that's how you get converges conditionally. If the absolute value series diverges and the original series diverges, then the whole entire thing just diverges. And so people then say, okay, well then why start with the absolute value series? Why not start with just the original series? And you could definitely start with the original series, but again, you're still going to about, half the time have to do 2 steps. So the other way to do it is if you looked at, I should put an or here. If you look at the original series, the summation of the a sub n's, so again, this could converge or it could diverge. And if it diverges, you're done. So if it diverges, then the whole entire everything diverges. But if it converges, now you have to look at the summation of the absolute value of a sub n. And that could converge or diverge. So if the original series converges, and then you look at the absolute value and it also converges, then you get converges absolutely. If the original series converges, but then the absolute value one diverges, you get converges conditionally. And so basically, what it's saying is that there are pieces in that original series. A lot of times this happens when you have an alternating series where pieces are canceling things out. And so it actually allows stuff to behave okay, to converge. But once we start just taking every single term, the absolute value of every single term, then it's not going to work out for us to converge. So that's what that converging conditionally means. And so the question becomes like, well, why do I even care about this, right? And so the thing is a lot of higher mathematics is built on series. So series run in the background through a vast majority of higher mathematics, especially calculus, okay? Does this mean from here on out in calculus you use series? No. But it means that the reason we can do the things we do in calculus is because of series. And not only just because of series, but because of absolutely convergent series. So to be able to do some higher level mathematics things that operate in the background behind calculus, you need series that are converging, and that are converging absolutely. So it's actually like an important, it's a very important concept. It's just that it's not super important when you're in Calc 2, right? So like when you're in Calc 2, it's like, yeah, I can figure out if a series converges absolutely or conditionally. It's not unless you happen to be a math major and you go on and take a lot more math that then you begin to realize, oh, this is why absolutely convergent and conditionally convergent is important. Oh, because a lot of mathematics breaks down if you don't have absolute convergence. This also brings up, like, you can find like YouTube videos where people are proving crazy things. Like they'll prove like 0 is equal to 1. Like, look, mathematically I proved this, right? And they use series. And the problem is they're using divergent series or conditionally convergent series to do it. So they get these crazy results and they're like, this is crazy, right? Like look, math can prove that 0 equals 1, you know? Math people have been lying to us, all this stuff. No, math cannot actually prove that 0 equals 1. It's just that you're using math that you don't understand, and you're using a concept, series, and you don't understand the implications of what you're doing. So those things exist out there, so just be aware of them. And they look pretty flashy. I had a couple years ago when I taught Calc 2, one of my Calc 2 students argued with me, and they, then they sent me the link to the video, and they were like, no, watch it. He does everything correct. And, and I had to be the bearer of bad news to be like, yeah, he does do everything correct in the video. The problem is that he's also using a series that does not converge absolutely. So what he proves, doesn't mean anything, right? It's like saying, well, if the sky was, neon yellow, then pigs fly, right? Well, our sky isn't neon yellow. So I could say anything I want because, the sky's not going to be neon yellow. So it doesn't matter what I say after that. So it's a good logic exercise. So if you're a math major and have to go on to take discrete math, you kind of talk about some of these implication things. Like if you assume something false to begin with, you can say anything you want. Anyway, all that you probably don't need to know for this. But basically these two flowcharts here, they're going to tell us how we're going to either work from one side or the other. So either we're going to look at the absolute value of the series, or we're going to look at the original series. It doesn't matter which way you do it. So if you want to pick one way and say, I am always going to start with the absolute value, I am always going to start with the absolute value series, that's completely okay. I personally, right, because I've been doing this a while, I can kind of look at a series and go, I think this series probably is going to diverge, so I'll start with this side, right, the right-hand side. I'll start with the original series. Or I look at it and I go, yeah, I think it probably will be okay in an absolute value, so I might start here. So it's kind of my way of being like, well, maybe I can bypass having to do two tests, but it still doesn't always happen. So we're going to do examples. But before I do that, questions. I know I just rambled a bunch. No? Okay. B, summation n equals 1 to infinity, negative 1 to the n, over square root of n. Oh, that's super laggy. All right, wait a minute. So I've got negative 1 to the n divided by square root of n. So again, so if we look at the absolute value, so that's going to be the summation n equals 1 to infinity, absolute value of negative 1 to the n over the square root of n. When I take that absolute value, right, the part that happens is the negative 1 part goes away. So we end up with the summation n equals 1 to infinity of 1 over the square root of n. Or we could rewrite this as the summation n equals 1 to infinity of 1 over n to the 1/2. So what kind of series is 1 over n to the 1/2? Yeah, it's a p series. Our p is 1/2. And what happens when p is less than 1 in a p series? Yeah, it diverges. Okay, so in terms of that flowchart, right? So I looked at the absolute value part, it diverged. So now I'm to the case where I have to actually look at the original series. So now we have to look at the original. So we've got the summation n equals 1 to infinity, negative 1 to the n over the square root of n. And we're going to do the alternating series test on this. Right, that negative 1 to the n is indication that it's an alternating series. So remember, for the alternating series, when you take away the alternating series part, the negative 1 to the n part, we want to make sure that everything that's left, so in this case 1 over square root of n, is positive. So that's true. We want to check, is 1 over the square root of n decreasing? And again, you can check a couple different ways, right? The way we were doing it kind of before was like 1 over square root of n, is that bigger than 1 over the square root of n plus 1? And that is, right? So as my bottoms get bigger, my fractions get smaller. And then the last thing, so like there's 3 things you have to check for alternating series. Right? So the last thing we have to check is the limit. So we're looking at the limit as n approaches infinity of 1 over the square root of n. And so what is that limit? Yeah, so that limit is 0, which is what we needed to happen, right? So it satisfies all 3 pieces. So the summation n equals 1 to infinity of negative 1 to the n over square root of n converges by the alternating series test. Excuse me. So the absolute value diverged, but the alternating series converged. So therefore, the summation n equals 1 to infinity of negative 1 to the n over the square root of n converges conditionally. Oh, excuse me. So converges conditionally. You could also say conditionally convergent. Either way works. Questions? No. So there's an example where you have to go through both things, right, to get it to work. So, let's do another example. Does anybody need me to wait before I go to the next page? Okay, so that was B, so C, summation n equals 0 to infinity of negative 1 to the n factorial over 2 to the n. So I look at this and I go, no, I don't know it. So I personally look at this and I go, oh, n factorial is super big, which means this is going to just blow up. So therefore, I probably could use a different test. And it's like, basically, it's probably going to diverge. And so since it's probably going to diverge, I might as well not look at the absolute value series first. I might as well look at just the original series. But that's just me. You could do the absolute value series, but you're going to have to check, but you potentially might have to do more work. So just so you kind of get the idea that you don't always have to start with the absolute value series, let's look at this series. So, okay, I'm given this series. I could do the alternating series test on it, but doing the alternating series test on this is kind of a little complicated. So the n factorial, anytime I see a problem that has an n factorial in it, my mind automatically goes to a certain test. Anybody want to guess what that test is? Yeah, so I automatically go to the ratio test, right? So we're going to hope that if we do the ratio test, we don't get 1, right? It's possible we might actually end up getting 1, but let's see. So let's try the ratio test. I like to try things with you guys. I should forewarn you, on my paper I did not use the ratio test. However, I like to try things with you guys because I think when you're at home, right, you're not like me where you're just going to look at a problem and be like, oh, boom, I'm going to use this. So instead, I gave you guys the idea that when there's a factorial, you should probably do a ratio test. So I kind of want to follow through with that and let's see what happens here. And it might not work out for us, and that's okay. I think it's helpful for you guys to see when tests don't work and what I do once something doesn't work. So, okay, so let's try the ratio test. So the ratio test says to take, look at the limit as n approaches infinity of the n plus first term. So n is the absolute value, right? So the absolute value of negative 1 to the n plus 1 factorial, divided by 2 to the n plus 1. So we take the n plus first term, and then we divide that by the nth term. So negative 1 to the n factorial over 2 to the n. Right, so that's what the ratio test just straight up says to do. The negative 1 to the n plus 1 part, we don't have to worry about that because it's inside an absolute value. And so since it's inside the absolute value, that part's going to just, the negative part is going to go away. So this is really going to be equal to the limit as n approaches infinity on the top, and everything else is positive, so I don't even need the absolute values anymore. So we're going to have n plus 1 factorial divided by 2 to the n plus 1. And then I'm just going to flip that bottom fraction right now. So it's going to be divided by 2 to the n over n factorial. And then this is where we're going to get stuff to cancel out for us. Remember, we talked about this last time. N plus 1 factorial is n plus 1 times n factorial. And 2 to the n plus 1 is 2 times 2 to the n. And I do that because now I can cancel things, right? The n factorials would cancel. The 2 to the n's would cancel. And so now I'm left with the limit as n approaches infinity of n plus 1 over 2. So questions about how I did any of that? Okay, so now if I take the limit, what is that limit? Yeah, that limit goes to infinity. Okay, how does infinity compare to 1? Is it less than 1? Greater than 1? We know it's not equal to 1. Yeah, it's bigger. So this is bigger than 1. Remember on the ratio test, when you have something greater than 1, it diverges. So what we're saying is the original series summation n equals 0 to infinity, negative 1 to the n factorial over 2 to the n diverges. And if the original series diverges, it's not going to converge absolutely or converge conditionally. It's just going to diverge. So you're just done. And the ratio test worked out here, right? Which was nice. I was trying to do the math for the ratio test in my head real quick. I had things. I didn't cancel something right. So I was a little afraid we were going to get one, but we didn't. Questions? Sure, yeah. So if I go back to the chart, we did this side. So I started with the original series diverged, and so we got here. So that's why I didn't have to do another test. If the original series diverges, it diverges. If I had started with the absolute value series and did a test and it diverged, then I would have had to look at the original series. But I started with the original series. That's why I didn't have to do another test. That's a good question. And it's hard to... That's why I draw these flowcharts, because I think when you see it as the flowchart, it makes more sense. If you had started with the absolute value, you would have probably done a ratio test for that, found it diverges, and then you would have had to go back and do exactly what we did and found it still diverges. So you would have gotten down here, it diverges this way too. Other questions? Yep. Okay. let's do another example. So D summation n equals 1 to infinity of negative 1 to the n over the natural log of n plus 1. Whoops. My natural log does not look like it's attached to the n plus 1, but it is. Natural log of n plus 1. Okay, so I'm going to let you guys tell me, what do you want to start with? You want to start with the absolute value series, or you want to start with the original series? So basically, do we want to start with the flowchart? Do we want to do the flowchart on the left or the flowchart on the right? It doesn't matter, but somebody's got to pick one. Okay, so if we did the alternating series, we're talking about starting with the right flowchart, right? So, we're going to look at the original, which is alternating series. Okay, so, here's my original, right? N equals 1 to infinity, negative 1 to the n, over the natural log of n plus 1. So we want to know 1 over the natural log of n plus 1. Is that positive? And you might say, well, when n is real small, it's not going to be positive. That's okay. So remember, it just has to be positive from a certain point going forward. So yes, this works. We want to know 1 over the natural log of n plus 1 is decreasing. So what do we think? As n starts getting bigger, right, do the terms 1 over the natural log of n plus 1, do they start getting smaller? Yeah. Right? So as n gets bigger, the natural log of n plus 1 keeps getting bigger, and then 1 divided by that is smaller. So yeah, it's decreasing. And then the third thing, so that was the first thing, is the positive. The second thing is it decreasing? The third thing is we have to look at the limit. So the limit as n approaches infinity of 1 over the natural log of n plus 1. And what does that limit go to? Yeah, so that limit goes to 0. Okay, so this all tells me that the original series converges. So we're on that left spoke, so it converges, which means now I have to look at the absolute value to determine if the absolute value series also converges. It'll converge absolutely. If the absolute value series diverges, it'll converge conditionally, right? So I'll come back to this page here in a second, but again, we are over on this side of the chart, right? We looked at the original one, it converged, and so now we have to look at these. We have to look at the absolute value one and figure out which situation we're in. So this series is either going to converge absolutely or it's going to converge conditionally. We just don't know which one yet. Questions? Okay, so now let's look at, the absolute value. So we're looking at the summation, n equals 1 to infinity, the absolute value of negative 1 to the n over the natural log of n plus 1. And that would turn out to be the summation n equals 1 to infinity of 1 over the natural log of n plus 1. Okay, so I have to figure out what to do with that series. So I have to use the series test, right? One of the tests we've been doing so far. Anybody want to take a guess as to what test I could potentially do? Okay, so that's a good idea. The problem is it's not exactly a P series because it's not just n raised to a power. You have a natural log, right? So the P series has to look like the summation of 1 over n to some power P. So I don't exactly have that. It's possible, like, it's a good thing to keep in mind in case we decide we want to do a comparison test, and we could compare it to a P series. But 1 over the natural log of n plus 1 itself is not a P series. So I think that maybe you guys, my guess is that you're kind of like, I don't know. I have no idea when I get to things. Yes, you can compare to 1 over the natural log of n. So let me give you a little bit of hints as to what I run through in my head when I'm trying to determine what to do, right? So when I'm trying to determine what test to look at, I go, okay, so first thing I kind of say is, do I think the divergence test would work? This right here, the fact that this limit goes to 0 is telling me the divergence test is not going to work, right? Because the limit here would go to 0, and that doesn't work for the divergence test. It's not a P series. It's not a ratio test, right? That leaves me with the integral test, but I don't know how to integrate that, so I'm not going to use the integral test. It's not really a great candidate for a ratio test. You might be able to do it, but it's going to take a lot of work, and so more work than we care to do. Everything is not raised to the nth power. That's when I do the root test. It's not an alternating series, so I'm kind of stuck with the comparison test, either the comparison test or the limit comparison test. So the idea is when you do the comparison test, you want to pick a series that you know what happens to it. And you kind of want to pick something that represents like the biggest thing. I usually think about doing the biggest thing on the top and the biggest thing on the bottom. So Sandra gave the idea of we could compare it to 1 over the natural log of n. And we definitely could do that. So we could do a comparison test. And we definitely could compare it to this, 1 over the natural log of n. The only problem with that is I don't know what happens with 1 over the natural log of n, right? It's now been a while since the last time we met, or when we did the comparison test. We might have done 1 over the natural log of n during, like, when we were in that section, in which case if we did, and we know what happens to it, we could definitely use it to compare to. But I try to pick something I kind of know. So rather than compare it to 1 over the natural log of n, something that's kind of potentially even better to compare it to is just 1 over n. So I could try comparing it to this, but I don't know what this does. So let's try comparing to summation n equals 1 to infinity of 1 over n. Yeah, so we're going to compare to 1 over n. All right. So now I want to look at, so first off, 1 over n. What does 1 over n do? We know 1 over n is a P series. P is equal to 1, and we've already even talked about this today, so it diverges. Okay. Yeah, so it's the harmonic series, it diverges. So now the question is, do you want to do the regular comparison test, or do you want to do the limit comparison test? Okay, the regular comparison test. So for the regular comparison test to work, since our series that we were comparing it to diverges, we want to know, is 1 over the natural log of n plus 1, is that going to be greater than or equal to 1 over n? Okay, so Robert says no. Does everyone agree no? Okay, so he's saying 50-50. Yeah, so I don't know. There's a couple things you could do, right? So one of the things that you could do is that you could cross multiply these, right? So basically we're looking at, is n bigger than or equal to the natural log of n plus 1, right? We know for a fact, you're allowed to use this fact. I kind of said this the other day. This doesn't quite exactly get us here, but you can use the fact that the natural log of n is always going to be less than or equal to n. Okay, Aiden said you could look on Desmos. Yeah, so you could graph these two. So when you looked on Desmos, does it look like 1 over the natural log of n plus 1 is greater than or equal to 1 over n? Yeah. You could also reason it out like a little bit. So I'm fine with any of those. You can look on Desmos, you can look on something, you can use my little hints here. If you think about it, the natural log of n, it grows pretty slow, right? N grows a lot faster. So you can kind of like in your head reason out and be like, yeah, I believe that n is bigger than or equal to the natural log of n plus 1. The other thing you could do, and this is not foolproof, but it works a lot of the time, is you could pick a big number to put in and test. So like 10,000, right? So is 10,000 bigger than the natural log of 10,001, right? And you could punch the natural log of 10,001 in your calculator and compare it to 10,000. So natural log of, I have a calculator right here. So if I punch in the natural log of 10,001, oops, I did 1,001. It's 9.2, right? So the natural log of 10,001 is 9.2. Is 10,000 bigger than or equal to 9.2? Yeah. If you're going to test it with a number to see if your inequality works, right here, so like I tested essentially that line there with a number, make sure your number's really big. So pick at least like 10,000. It's not a foolproof way to do it, but for the stuff we're dealing with, it usually generally works out for you. So, okay, so it's bigger, right? Which means that this tells us that this summation and our series, the absolute value series, -1 to the n over the natural log of n plus 1, diverges. So the original series converged, but then the absolute value series diverges. So therefore, the original series we were given, -1 to the n over the natural log of n plus 1, converges conditionally. I don't know why I have such a hard time writing conditionally. Like my conditionally just doesn't want to look like a conditionally. Questions? So this converging conditionally or convergent absolutely generally happens with these alternating series, right? You can look at other series to determine, do other series converge conditionally or converge absolutely. But most of the time we're asked about whether or not they converge conditionally or absolutely is when we have these alternating series. And what we're going to do next class ends up generating a lot of times alternating series, and that's why we need to be able to look at this. That being said, using this idea, anytime you can show that a series converges absolutely, then you for free get that the series, just the regular series, converges. So converging absolutely is like more powerful. So if you converge absolutely, then you also converge just under regular conditions. So that's kind of, okay, so converging absolutely implies the original series converges. Whoa, that's super slow. I've been done writing for a good amount of time. All right, let me. So converging absolutely implies the original series converges. So sometimes you're just asked, you're not asked, like on the homework, right? I asked you, do the alternating series here converge or diverge, right? So that's just straight up applying the alternating series test. Then I gave a chunk of problems where I said, determine if the following converge absolutely, conditionally, or diverge, right? And so when I care about whether something converges absolutely or converges conditionally, I'm going to ask you explicitly to tell me, does this converge absolutely or converge conditionally? However, sometimes you're just given problems where you just asked, hey, does this converge or diverge? And it's kind of hard to figure out what's happening, but it's easier to figure out what's happening when you look at the absolute value of the series. So this absolute convergence can actually help you out. So we're going to do a couple, so 2 examples where absolute convergence helps us. So for example, determine if the following converge or diverge. So A, summation n equals 1 to infinity of sine n over n squared. Okay, so the problem here is the sine n, right? So sine is a periodic function, right? So it bounces back and forth between 1 and minus 1, but it keeps going up to 1, down to minus 1, up to 1, down to minus 1, over and over and over, back and forth. So the terms of this series keep getting positive and then negative and then positive and then negative, but it's not an alternating series. Things don't go strictly positive, negative, right? You're going to get you might get a bunch of positive terms and then a bunch of negative terms and then a bunch of positive terms and a bunch of negative terms. So this series, just as it is, like, it's kind of hard to figure out what happens to it. None of the tests that we have actually work on it. But instead, we could look at the absolute value of the series. So if we look at the absolute value of sine n over n squared. And so you may go, well, how does that really help me? Well, it actually helps us a lot. The reason why is because the absolute value of sine n, right? So now you're talking about just positive numbers between 0 and 1. And so that kind of sets you up really well to use the comparison test. So I could compare to the summation n equals 1 to infinity. So the biggest the top ever gets now is 1, and the bottom is n squared. And all the terms are positive, since I have that absolute value. 1 over n squared, that's another p series. P is equal to 2. 2 is bigger than 1. So does it converge or diverge? Yeah, so it converges. And so if you're doing the comparison test and the series you're comparing to converges, we want to know, is our original series sine n over n squared, is that always less than or equal to 1 over n squared? And so this one's actually pretty easy to figure out. The bottoms are the same, right? So I have n squared on the left piece and n squared on the right piece. So the bottoms are the same. So really, I just have to ask myself, is the absolute value of the sine n always less than or equal to 1? Yeah, right? So is this less than or equal to? Yeah. So therefore, the summation n equals 1 to infinity of the absolute value of sine n over n squared converges. Right? And since the absolute value converges, then the summation n equals 1 to infinity of sine n over n squared converges absolutely. So it definitely converges. Right? So absolute convergence is a stronger type of convergence than when we just say, oh, this converges or this diverges, right? Converging absolutely is stronger. But the idea here is that absolute value sometimes like helps you out. Questions? And I have one more here where the absolute value is going to help us out, where it's not exactly an alternating series, but it kind of looks a little bit like one. Does anybody need me to wait a minute before I go on? Nope. Okay, so B, summation n equals 1 to infinity, negative 1 to the n times n plus 1 over 2, all over 4 to the n. So again, this series kind of looks like an alternating series, but it's not exactly an alternating series. It's not going to bounce back and forth between a positive term, a negative term, a positive term, and negative term, because you have this n times n plus 1 divided by 2. And I should say that I took this problem from a book someplace, but if you actually stop and think about it, n times n plus 1 divided by 2 is actually always going to be even. N times n plus 1 is always even, but when you divide by 2, okay, never mind. It's like the beginning back from spring break, so my brain's still trying to catch up with not being on break here. Okay, anyway, yeah, it's not necessarily going to bounce back and forth between positive and negative terms. So I can't just do the alternating series test, but I could look at the absolute value of this, because the absolute value of this is still going to do the same thing. It's going to get rid of that negative 1 part with this like weird exponent. So when I do the absolute value, it basically gets rid of the negative 1 part. So I end up with just 1 over 4 to the n. And what kind of series is that? Yeah, that's a geometric series. So this is summation n equals 1 to infinity. It's really 1/4 to the n. So it's geometric. Not n. R is equal to 1/4. So the absolute value of 1/4 is 1/4. And 1/4 is less than 1. And then when the R value is less than 1, it means it converges. And so so our absolute value series converged. So that means, therefore, our original series, n equals 1 to infinity, negative 1 to the n plus 1 over 2, all over 4 to the n, converges absolutely. So it definitely converges. Remember the instructions here didn't ask whether something converged absolutely or not. It just asked, does it converge or does it diverge? So this converges. Questions? No. Okay, so that's the end. That's absolute and conditional convergence. So that's all I was going to go over today. Like I said, next class we're going to come in and we're actually going to look at series a little bit differently. So we're going to look at some other stuff dealing with series and some other ways of kind of using series. So it's interesting stuff. But yeah, this is all I was going to do today. So if anybody has questions, you can feel free to hang around and ask me questions. Otherwise, like, if you don't have any questions, you're free to go. So